Hello and welcome back to Calculus 1. We are talking about implicit differentiation, which is a natural way to extend the chain rule. So far, we only talked about the derivative of the function in respect to x. And in a chain rule, we saw that we can take the derivative in respect to even a whole function. So now implicit differentiation is going to pull us away from the world of functions, and we are going to take derivatives of expressions which are not functions, or relations that are not functions. So we will be able to differentiate circle and things like that. Now, where is this idea coming from? Well, if you have your good old function f of x, which you are all used to, you know y is equal to f of x, and then you can take the derivative, so dy dx will be f prime. And we know that there is a derivative here because we can draw these tangent lines. No matter where you put a point, you can draw the tangent line. But then, when you are in xy plane, and you have a different kind of shape, that it's definitely not a function because it fails vertical line test, this thing still has tangent lines. That's also a tangent line. And if there is a tangent line, y equal mx plus b, that m slope is actually the derivative computed at point A. So there has to be a way to take the derivative off of the relations that are not functions, because we see that the tangent line, the slope, all of that stuff exists. So let's see how we do that. Before we start, I want to one more time talk about notation for the derivative. We know that we define derivative through that limit that we are not using because we learned all the shortcuts. So that's the first concept. Then we say that if you take the derivative of f of x, you will get the derivative. So that's the notation, right? We also know that we can use Leibniz notation, which is dy dx, because this y is actually f of x, which tells us that there is a multiplication here, which we don't write in between d dx and x, f of x. Further, this part over here is called the differential operator. See, you have operations like addition, multiplication, squaring. You have operations which will combine two or more numbers to change numbers. You put in 2 plus 5 and you get 7. You change number 2 and the number 5 into number 7. And that is done using operations. You can divide 2 by 5. You can multiply 2 times 5 and get 10. So operations change numbers. Operators change functions. So we will see that derivative and integral are operators. So now, when we learn that part, we understand that the differential operator, which is d dx, is changing the function x squared, which is quadratic, into 2x, which is linear. So operators change functions. Now I can apply multiple operators like this onto a function, and then you will do one at a time. So first you will do the inner one, so you copy the outside d dx, and then you get 2x over here, and then when you take another derivative, you get 2. What you actually did here is the second derivative, and we can combine that operator using notation by simply saying d times d is d squared, and dx times dx is dx squared. So d dx is like an instruction. Take the derivative. Take the derivative of x squared. That's what d dx is. And you know about the instruction, like license and registration. That's instruction, right? You don't go and fetch the ice cream. You fetch the license and registration. So d dx is the operator, which literally means take the derivative of whatever is following it. And you can have a bunch of them linked together for the second, third, fifth, 30th derivative, and so on. Now, important kind of thing is to see how this works. Every time when you differentiate, the chain rule pops up. So if I am to differentiate, let's say y equals x squared, I will say dy dx is equal to 2x, and then you can still write dx dx, but we don't write that because that cancels to 1. What this says, the thing that we never write, this says we took the derivative in respect to x. Observe that on the left-hand side, where you took the derivative in respect to x, it didn't cancel because it's dy and dx, those are different. So now, if I am to dig deeper into this, look how nicely notation works. If I am to say d dx of y on the left-hand side is equal to d dx of x squared on the other side. Now, on the left-hand side, clearly it's just dy dx because there is that times in between. So you call it just dy dx. There's a little bit more to it, but we'll see it soon. And on the right-hand side, x squared becomes... Oh, hold on. No, I gotta do it. So on the left-hand side, you would say the derivative of y is 1 times we took the derivative of y in respect to x. On the right-hand side, the derivative of x squared is 2x, and we took the derivative of x in respect to x. So if you pay attention, on the right-hand side, your variable is x. On the left-hand side, your variable is y. But you are taking the derivative in respect to x. That's why you're writing over dx. So when you are looking at the left, you see that when you take the derivative, you put the instruction in front, which is d dx. And then you say the derivative of x, the derivative of y, the derivative of g, whatever you have there as a variable, the derivative of that is always 1, right? And then you say, I took the derivative of y in respect to x. On the right-hand side, you have x squared, whose derivative is 2x, and then you took the derivative of x in respect to x. So now, on the left-hand side, dy dx remains, and on the right-hand side, these guys cancel. And this is actually what's happening in the background. So we never write this dx over dx. Now, left-hand side is a chain rule, because y is the function of x, and this dy dx piece is the chain rule piece. So we can understand it either as a chain rule piece, or we can look at it as, okay, I took the derivative of y in respect to x, so dy dx is there. Let me solve another problem. Say y is equal to 3 cosine x. What I'm going to do is I'm going to put the differential operator on both sides. I'm differentiating. On the left-hand side, I have 1 times dy dx because derivative of y is 1, and I follow with dy dx because I took the derivative of y in respect to x. On the right-hand side, I will copy 3, and then derivative of cosine x is negative sine x, and then I say I took the derivative of x in respect to x. So now final version over here is dy dx is equal to negative 3 sine x, and these guys canceled, so that's it. Now I understand that you are already proficient to go from this step here because you practiced basic derivative. But we are now just shining a new light onto a technique that you already know, emphasizing this idea that you can still take the derivative of y in respect to x. So now I would like to see if I can push this further. So behold the circle. Now, the circle has equation x squared plus y squared equals to whatever, 4. Yeah, 4. Now we know that circle is not a function. So you cannot take the derivative in the regular way, regular manner. But you still know that circle has all the tangent lines, so derivative must exist. So what you are going to do is you are going to force the derivative on the entire equation and go do the derivative term by term. So what I'm going to do is I'm going to enclose the entire relation in these brackets and put the instruction to take the derivative in front. And now we do the derivative term-wise. What is the derivative of x squared? 2x. And we took the derivative of x in respect to x. Awesome. Plus, what's the derivative of y squared? 2y. And then we took the derivative of y in respect to x. Equal to, what's the derivative of 4? 0. Nice. Now we also see that dx drops. So now what is left? All it's left is to solve for dy dx, right? You see that there is a dy dx, just massage this equation to get dy dx equals everything else. So what I have is 2y dy dx is equal to negative 2x when I move it to the right. And then I divide both sides by 2y to get dy dx is equal to negative x over y. And that's the derivative. Now observe that this derivative depends on x and y. It doesn't depend only on x. But this is what we call the implicit differentiation. You go term by term, and you can differentiate anything, whether it's a function or not a function. Implicit differentiation works all the time. So now that I have dy dx, I can figure out slopes, I can figure out the equations, tangent lines, and all of those good things. So let's take a look at a different case. Say that you have a relation that says 2x minus 3 cosine y is equal to y squared plus 9. we can ask software. You hopefully all installed Mathematica and you have access to it. You could just type in graph and just type all of this in and hit enter. It will come up with some kind of curve. Now I want to know what the derivative of this is. So what I'm going to do is I'm going to again enclose the entire thing into these brackets and put the instruction in front. Take the derivative of every term independently. That is implicit differentiation. Cool. What's the derivative of 2x? 2. So 2, and I took the derivative of x in respect to x. Awesome. Moving to the next term. What's the derivative of cosine y? Negative sine y. And then I follow with the chain dy dx because I took the derivative of y in respect to x. Equals to, on the other side, derivative of y squared is 2y, and then I still follow with dy dx because I took the derivative of y in respect to x. And then plus 0. We don't put anything there because the derivative constant is 0. So now dx and dx drops. We just get 2 plus 3 sine y dy dx is equal to 2y dy dx. Now what? How do I fish out derivative equals everything else? What should I do? I'm sorry? Very good. You will combine all terms that have dy dx on the same side and push all of those without dy dx on the other so that you can isolate by factoring dy dx. So we are going to move negative 3 sine y dy dx to the other side. To get 2 equals 2y dy dx minus 3 sine y dy dx. At which point we factor out dy dx, and we are left with 2y minus 3 sine y. What is the last step I have to do to get dy dx alone? Divide. Very good. So finally dy dx is equal to 2 divided by 2y minus 3 sine y. A little bit of mathematical, a little bit of algebra, but we solve for dy dx because the slope is equal to. So it doesn't matter how many of these dy dx's you end up with, as long as you put them all on the same side, factor it, and divide with whatever else you get in the parentheses, you are good to go. That's all it is. So now all we need to do is bunch of problems, find some tangent lines, combine this with product rule and other cool things to make it annoying. If you understand the concept, if you understand that you are taking the derivative term-wise, and if you understand that you have these every time you take the derivative, because those say I took the derivative of x in respect to x, I took the derivative of y in respect to y, because you will either be taking the derivative of x or y. You can't be taking the derivative of both of them at the same time. So as long as you are trained to, right, and then anytime you take the derivative of x term, you can just skip writing dx over dx because you know it's going to cancel to 1. You're not going to see the book does it or do it, or you know, if you go to tutoring center, no one will do it because no one does it. But it's there, right? It's there. We don't write it because it cancels to 1. All right, let's take a look at example that we can pick up in textbook. So they gave us these wonderful examples. And now they want you to also compute the derivative because that gives you the slope. So give me a problem 7 through 12. And it is. You know how to pick it. Problem 10 in the textbook. Square root of x minus 2 square root of y is equal to 0. And they want to find the slope at 4, 1. Notice how they gave you x and a y. So your job is to find the derivative, and then once you have the derivative, you plug in the point to get the slope. All right, let's see. So what is the well, we will take, let's first write, we will take the derivative of each term independently. What's the derivative of root x? Yes, you are memorizing this one because there's shows up way too many times. And then we have dx over dx because we took the derivative of x in respect to x. And that will cancel. And then we have the derivative of negative 2 root y is? Simplified, yes.
1 minus 1 over y.
Yes, because the half and the 2 will cancel. And then we took the derivative of y in respect to x. And then on the right-hand side, derivative of 0 is 0. So now, what do we do? Very good. So we have 1 over 2 root x is equal to 1 over root y dy dx. And then we multiply both sides by root y. That will cancel on the right. Of course, it's math. And we have square root of y divided by 2 square root of x, or if you want to be fancy, 2 square root of y over x. You have x, you have y. So now, your dy dx is 2 square root of y over x. M is going to be when you plug numbers in. So now we got that the slope is 1.
Before you did the 2 square root y over x, plug them into the first one.
You can plug into anyone. Yeah.
But it comes out as 1/4, right?
Mm-hmm.
1/4 doesn't equal 1.
Half times 2 is. What do you mean rule?
So like when you do the when it's the square root of y over 2 over square root of x, you change it to 2 times the square root of x over y.
Oh wait, yeah. Hold on. It's not 2 times. It's 1/2.
That's why it comes out to 1/4.
Yep.
Thank you.
Yeah, that 2 was in the denominator. It stays in the denominator.
So m is 1/4.
Slope is 1/4. Yes. All right. You.
Like you can still just combine them like that.
Yes, that's the algebra rule. All right, let's take a look at spicier examples. How about xy minus 3y squared is equal to sine y plus 9x. Suggestions? Yeah. What should we do?
Should we treat x, y as a multiplication and do it separately?
Should you?
I'm asking.
Yes, you should, because it is x times y. Now y is a function of x, so what's that? It's a product rule. Nice. So the first term is a product rule. The other ones, easy. So let's do this together. You had ample time to finish it. Copy the first one, which is x. The derivative of y is 1 times I took the derivative of y in respect to x. Plus, copy the second one, which is y, times the derivative of the first, which is x. Derivative is 1 times I took derivative of x in respect to x. So that's the product rule. And every time I took the derivative, you see me following with the chain of what I actually did. So copy x, derivative of y is 1, and then dy dx because we took the derivative of y in respect to x, plus copy the second one, which is y, and then derivative of the first, which is derivative of x is 1 times dx over dx because I took derivative of x in respect to x, minus 6y, and then dy dx, very good, equals to, on the other side, we have a cosine y dy dx plus 9 dx dx, right? So what do we have? We have x dy dx plus y minus 6y dy dx equals to cosine y dy dx plus 9. We move all of the terms with dy dx to the left, all of the terms without dy dx to the right. So on the left, we can also factor at the same time. We already have the first term is x minus 6y and then minus cosine y when it moves to the left. On the right hand side, we simply have 9 minus y. So dy dx on its own is 9 minus y divided by x minus 6y minus cosine y.
Wait a second. So what if I what if I left the y on the left side and I moved the dy dx to the right side?
All of the signs would be opposite. In the numerator and denominator, all of the signs would be different, and if you factor out minus 1 on top and the bottom and cancel it off, it will look exactly the same. So you either have 9 minus y on the right, or you have y minus 9 on the left. They're exactly negative 1 multiple of each other. Matt?
What's the product rule on the xy term? Why is the x dy over dx and the y dx?
Copy the first. Derivative of the second. Copy the second times the derivative of the first. Now over here we took the derivative of y in respect to x, and over here we took the derivative of x in respect to x. Just keep track of what you took derivative of in respect to what. That's what that changes. You say I took the derivative of x in respect to x. Because look, in this one you said derivative of y is 1. Derivative of y squared is 2y. Derivative of y cubed is 3y squared, right? Because you're taking the derivative of y, you take the derivative, whatever it is, and then you say I took the derivative of y in respect to x. When you did the other way, you were taking the derivative of x, so you took the derivative of x.
Wait.
There you go. So.
So basically, this should have this. No. Is that right?
Yes.
I just have that's what you did. If I wrote this, I'm supposed to simplify it so that it ends up being.
No, it's the same. There's nothing, you don't have to type it.
Your answer was y x minus 6y minus.
That was my fault. It was 9 minus 5. Opposite zero. They're both opposite.
Okay.
They all have different signs. You pull minus 1 on top and minus 1 on the bottom, you will get my answer. And those minus 1s cancel because you have 1 on top and 1 on the bottom. If only one sign was different, then you would be wrong. Because all of the signs are different. Correct. Right? Yes. Oh, perfect. There you go. Left is right, right is left. That's actually amazing. I never heard anyone say that. That's really good. Okay. By the way, how are we doing here? Still alive. Okay, good. What else do we have? Here's question 30. Find the equation of the tangent line at the point 1, 2 for open parenthesis x squared plus y squared close parenthesis everything squared equals to 25 over 4 xy squared. So find the equation of the tangent line. What are the steps? Derivative. Steps are the same like at the beginning of chapter 3. Tangent line procedure is always the same. Find the derivative, plug the point to get the slope, and then find the b. One.
So the first one would be x squared as the first derivative, or
What do you mean?
like do we treat it as a chain, or do we
You can.
any other way?
Oh, yeah. You can FOIL it, right? So you don't have to change it.
Okay.
Because it's square. If you move to the 20th power, then yeah, do the change.
Okay. So that is squared. Okay.
Well, it's easier to, if you FOIL, it will be easier. But it can be done. Some things you never forget. That's not wrong. Never heard anyone say that.
So Professor, the only space is two, the only space in our problem.
Yeah, right. It's not very hard.
So much work.
I want to do the popsicle. It was the same answer.
When I was finding derivatives for this, I got all of this, but then what do you do with the 2 off of it? Do you put it all together?
The suits. Right? The constants can be kicked outside. The constants get to be kicked outside. You do the derivative, and then you can apply the constant back. Fair?
So do you want it in that points format?
Well, you can write it y equal mx plus b. I'll have to check. I'm still working on the thing, so I'm not sure if that's correct, but I have faith it should be.
That x squared. X squared times 2y. Now that was later over here on this 2y. On this 2.
So as you can see, I distributed on the left. There was a product rule on the left and on the right, so you have to do it carefully. And then the last line I have is simplification. I just cleared some terms out and got all of the dx over dx out and so on. Now, your goal is to compute the slope. And you have the point given, 1 and 2. You don't have to go through crazy algebra to solve for dy dx actually now, because you already have everything you need. You can do substitution right here and cut your work significantly. You can plug your values 1 and 2 and replace every dy dx with m, because as soon as you replace x's and y's with numbers, you are replacing dy dx with m, because now you're computing the slope. So the point is 1, 2. So each x becomes 1. So the first term is just 4, plus the second term is 8m, plus the next term is y squared 4, 16, plus the next term is y cubed, that's 8 times 4, 32m. On the other side, we have y is 2 cancels, so 25m. plus, and then y squared, this becomes 4050. So what I did is I plugged in 1, 2, and m where they belong. So 8 plus 32 is 40. So you put all m's on one side. So that's 40 plus 20. 40m plus 20 is equal to 25m plus 50. So now you move 25 to this side, you get 15m. And move 20 to the other side, you get 30. And m works out to be 2. You also have a point 1, 2. So y equal mx plus b, or whatever other formula you want to use or like to use. So y is equal to the slope is 2, x value is 1 plus b, y value is 2. So b is 0. And sounds that the tangent line at 1, 2 is y equals 2x. Cool?
That's a lot of spice for y equals 2x.
Oh my god. Every time someone says something like that, I remember a time when I was in high school and the solution to the equation was 0, and I posed the philosophical question, why bother solving the equation if the solution is nothing? And the immediate response from the teacher was, get out. It was so short and simple. To the point.
Should there be a question like that on the exam?
Yes, definitely. You might want to start this one. Yeah, you got this.
Professor,
Yeah.
question. Y equals 2x because we put m as in 2 and b is a 0?
Yes.
Okay.
So this tangent line goes through the origin. How does this look like? That's the graph for this function. It's not a function. It's a curve. That's how it looks like. Let's see, do we have any? Maybe I should actually draw the tangent line as well. Whatever, it should go through 0. Anything else? They just have some crazy problems for no reason other than to annoy people. So one more and then we'll move to the next concept. Square root of x plus y squared is equal to sine y. So find the derivative in respect to x, obviously. Now, right, let's take a look at this together. We have a derivative of a square root. That means 1 over 2 times the square root times the derivative of the inside, which is 1 plus 2y dy dx. Right?
So why are you doing the derivative of the inside?
It's a chain rule. All of the rules apply.
Yeah. Wait, so is that a y or it's that?
Is that a y?
No,
There's
no.
a y over here and y over here.
No, I
and
didn't see
y
that.
over
It's
here,
two
and y over
connected
here,
to
and
them.
y over here, and y over here, and y over here.
No, it's that one. I didn't notice there's two connected to the y.
Ah. Yeah, I didn't understand. I didn't understand. Now we have to fish out dy dx, but this problem is not done. I just wanted to verify your first step, because we use the chain rule, and now all you need to do is to see, if you go and you distribute this twice, and you just multiply this on this side, right? It's called algebra.
No, I got it. I just kind of just took the rest.
So, algebra.
That sounds like how you do too much.
It's like a wolf and just stop talking to him.
He tries to get ghost, but they keep coming back.
Yeah, I'm stuck on this part.
So, yeah, it's easier, right? Usually those strawberries have to be done with the water. Like a 7 days, basically exactly how.
No, if it's like, say leave overnight, I want it, like, I kind of.
When you distribute
yeah, no,
set the counter, see why dy is dx.
But this is higher.
Well, this,
I wanted to have one
it's
at
the
the
same
same
thing,
time.
but here you can cancel it too, so it's just y over root x plus 1 squared. The whole thing.
So I will multiply both sides by 2 times square root of x plus y squared, because I really don't want to distribute that. And then move terms to the same side. And from there, dy dx, which is the slope, which is the derivative, is 1 over 2 square root of x plus y squared cosine y minus y.
How did you get to that on the left side?
Like
plus
this.
2y.
1 plus 2y dy dx?
Yeah.
That's a chain rule derivative of the derivative of x is 1, derivative of y squared is 2y dy dx. Chain rule. Okay? You see it?
Yeah, what
I don't
happens to
understand how you got to the next part after.
what happens to the 1 over 2 root x plus y squared?
What exactly happened?
You mean what's happening next step? Not the one that I...
I feel like there's like 2 in between. The 1 over
I just
2
multiplied both sides by 2 square root of x plus y squared.
Oh, okay.
Because that will cancel on the left, the denominator, and that's why it pops up on the other side right here.
Oh,
Okay. I just completely missed that.
Cool. They also have rational exponents in this section, so let's do nothing special, but yeah.
Professor,
Yes.
I really don't get this. Could you please step by step show me? Because I know
Which one?
we went with the chain from the beginning,
All right.
but what exactly happened?
So we are taking the derivative of two terms. We have a square root on the left and sine on the right. So we only have those two. On the left, when I take the derivative of square root, it becomes 1 over 2 times square root.
So why are we taking just over square root and
Because, well, you have the square root, so you have to take the derivative of it. So the square root is the main function. And then it has x plus y squared plugged into it, so it's a chain rule. So the second part is the chain rule, which is the derivative of the inside of the square root. Derivative of x is 1, derivative of y squared is 2y dy dx. That's the chain rule part.
the rest again? That is first part.
Well, the first part should be clear, because the derivative of square root of x is 1 over 2 root x. There's nothing else there. It's exactly what I have.
So we're treating the x plus y squared as the x.
Well, let me put it this way. And I can plug in whatever you want.
Okay.
Awesome?
Yes.
You can use a flower, but it's easier to draw. So it is the form. It is the form. The derivative of a square root is 1 over 2 times square root. So whatever mess you have here is that one. And then followed by the chain, which is the derivative of it. Right hand side easy, right? Now, when I delete these purple marks, we multiply both sides by 2 square root of x plus y squared. Because well, my denominator just disappeared. Hey, stop doing that. So I multiply both sides because this is multiplication here. I multiply both sides, that dies completely, as you can see, so just this is left. And on the right hand side, that thing is plugged in, and there's your cosine and there's your. Put these guys together on the same side. This is all one thing now, because times and times and times, it's all one thing. This goes there. There's a minus 2y, factor of dy dx. Number 1 stays on the left. And there you go. Awesome?
Yes.
Let's see what. So here are some of the problems that are not implicit differentiation, but you can do chain rule. So problem 41. Find the derivative of fourth root of a quotient. Yes. What happened? Yes. Chain rule is the main, right? Because of the fourth root, and then you have the quotient. Better. So this is more of a review of the last section. We rewrite this quickly as the 1/4 exponent, and we just go from there. Ah. See you next week.
See you next time.
I actually don't need these parentheses. Oh. So if you flip the thing, you lose the negative. That's the algebra rule. And then you have 8x minus 6 minus 8x over 4x minus 3 squared. These guys cancel. So what we have is negative 6 over 4, which cancels later, times 4x minus 3 over 2x, and then times 1 over 4x minus 3 squared. So negative 3 halves. And then we have 1 over 3/4. That will be 5/4, right? And that's it. So let's take a short break. After that, derivatives of logarithmic and exponential functions. Fun. Bye, stream.